So today we're going to do some pandemic math. In particular, we're going to learn what is the connection between R0 and herd immunity. Now, before I define R0 and herd immunity, let's define a few terms that will be useful for us moving forward. So the first term I want to define is X. What is X in this model? Well, X is just a fraction of the population that is susceptible to infection. So this is the fraction susceptible to infection. So if we are considering, for instance, COVID-19, but this model doesn't have to only apply to COVID-19. You can apply this model to any infectious disease. But if you're considering COVID-19, and let's say you have some population, and let's say 90% of the people in that population are susceptible to infection, then X would be equal to 0.9, because 0.9 is the decimal representation of 90%. So it's basically the decimal representation of the percentage that is susceptible to infection. So now that we've defined the fraction that is susceptible to infection, let's define Y as the fraction of the population that is immune to infection. So this is the fraction immune to infection. So once again, if we consider, for instance, COVID-19, let's say some people have already gotten COVID-19 and, they got better. And let's say if you've already had COVID-19 and you got better, let's say that develops some immunity. That is not necessarily true. I'm not, this is a math explanation. This is not a biological explanation, but let's just assume that if you've gotten COVID-19 and then you got better, then let's say you develop some immunity to COVID-19, then let's say 10% of a given population is immune. That would mean Y is equal to 0.1, because 0.1 is the decimal representation of 10%. Okay, so now that we've defined X and Y, how are X and Y related? How are X and Y related? Well, it must be true that X plus Y is equal to 1. Why? Well, X is just the fraction that is susceptible to infection. So X is the fraction of the population that can be infected. Y, on the other hand, is the fraction that cannot be infected. So the fraction of people that can be infected plus the fraction of people that cannot be infected must, of course, be equal to 1. Because the percentage that can be infected plus the percentage that cannot be infected must be equal to 100% of the population, and the decimal representation of 100% is just equal to 1. Okay, so now that we've defined X and Y, and we've defined how they are related, let's go back to the question, what is the connection between R0 and herd immunity, and define R0. So what is R0? It's called R0, first of all, because this is just a 0, and another word for 0 is just not. So what is R0? Well, R0 is just the basic reproductive number. Now, what is the basic reproductive number and why is it so important? Well, the basic reproductive number is the number of infections, or rather the number of people, an infected person would infect if everyone was susceptible. So think about this definition for a moment. R naught is the number of people an infected person would infect if everyone was susceptible. Now, obviously, this is an average figure, right? Like this would be an average for a given population. So think about the beginning of the COVID-19 pandemic. At the beginning of the COVID-19 pandemic, there must have been one person, that first person that was infected with COVID-19, and then that person spread it to the rest of the world. So when that first person was infected, in that population, that person was walking around, basically everybody else except that person was susceptible to being infected with COVID-19 because none of those other people, let's just assume that's true. I mean, the origins of COVID-19 are not exactly very well defined, but let's just assume that wherever this person was walking around, everybody they could have come into contact with was susceptible to infection. So at that moment in time, basically the disease was spreading at R naught. That first person spread it to R naught people, and every one of those people spread it to R naught more people. So let's say if R naught for COVID-19 is 2.5 in that population, then that first person spread it to 2.5 other people on average. Now, I'm going to talk about what that 0.5 means in a moment, but let's say that first person spread it to 2.5 other people, and then every one of those people spread it to 2.5 other people, etc., etc. Now, how can a person spread a disease to half a person? How can one person spread it to 2.5 people? I mean, spreading it to 2 people makes sense. Spreading it to 3 people makes sense. How does spreading a disease to 2.5 people make sense? Well, remember that R naught is an average number. And an average number does not have to be a number that is actually going to hold in reality. So it doesn't have to be a whole number in this particular case. So just to give you an example, think of a person and a dog, and ask yourself, what is the average number of legs between a person and a dog? Well, a person has 2 legs and a dog has 4 legs. So if you sum up the 2 legs plus the 4 legs, there's 6 legs in total if you take a human and a dog. Now, what is the average? Well, you only have 2 mammals here. You have 1 human, 1 dog. So you have 6 divided by 2. You're going to end up with 3 legs. On average, a dog and a human has 3 legs, but neither a dog nor a human actually has 3 legs. A human has 2 legs, a dog has 4 legs, but on average between them, they have 3 legs. So if the R naught value is something like 2.5, that's what it would be like on average. That means that if you had 100 people infected, on average, these 100 people would infect 250 other people. Now, this is the basic reproductive number. So this number assumes that everyone in the population is susceptible. This is different from the R value. Now, what is the R value? The R value stands for the effective reproductive number, as opposed to the basic reproductive number. The effective reproductive number. And the effective reproductive number is the number of people an infected person number of people an infected person would infect taking into account the fraction that is susceptible. Now, what does that mean? Well, it just basically means that the R value is like the R naught value. It is the number of people on average, the number of people an infected person would infect, but the R value takes into account how many people in the population are actually susceptible. So how many people are actually susceptible? Where the R naught value just assumes that everyone is susceptible. But obviously, during the course of an epidemic or during the course of a pandemic, the fraction of susceptible people is going to change. So that means that the R value is going to change, but the R naught value is not going to change unless there is some sort of behavioral change or some cultural change in the population that would inherently change the R naught value, or maybe some change in the disease, the infectivity of that disease. But just purely because people are becoming immune to the disease, the R naught value will not change, whereas the R value will change. So how is the R naught value connected to the R value? Well, the R value is equal to the R naught value times X. X, recall, is the fraction of the population that is susceptible to infection. So as you can see, at the beginning of the pandemic, when everyone is susceptible and X is equal to 1, you're going to get R being equal to R naught. But let's say over time, 50% of the population becomes immune. So Y becomes 0.5. That would mean, according to this equation, that X would have to also become 0.5. And if X is equal to 0.5, that would mean that the effective reproductive number, R, is only going to be half of R naught. It's going to be R naught times 0.5, so half whatever the basic reproductive number happens to be. Now, let's play a little bit with this equation in order to get the connection between R naught, or the basic reproductive number, and herd immunity. So come back to this basic relationship between the fraction of the population that is susceptible and the fraction that is immune. You can take this equation and you can rewrite it by subtracting y from both sides in order to get x is equal to 1 minus y. I just subtracted y from both sides and I arrived at this equation for x. What is this equation telling you? Well, this equation is telling you that the fraction of the population that could be infected is equal to the whole population minus the fraction that cannot be infected. So it's just rewriting this original equation by solving for x. And now if we have x is equal to 1 minus y, let's go ahead and take that and plug it in for x in this relationship between the effective reproductive number and the basic reproductive number. So what we're going to get is that r is equal to r naught times 1 minus y. Remember, all I did here is I just substituted 1 minus y, so the whole population minus the population that is immune, for the population that is susceptible. Because the population that is susceptible must be equal to the whole population minus the population that is immune. Now, let's ask ourselves at this moment, what must R be? What must the effective reproductive number be in order for the disease to peter itself out? So what must R be in order for the disease to over time become eliminated from the population? Well, it's obvious that R must be less than 1. Well, why? Well, what is R? R is effectively the number of people an infected person will on average infect. So if an infected person on average infects less than one person on average, then over time that disease is just going to become eliminated from the population. Imagine you start off with 100 infected people in a population. Well, then if R is 0.9, let's say, and 0.9 is less than 1, then those 100 people are going to infect only 90 people. And then those 90 people are only going to infect 81 people. And so you're going to get an exponential decline in the number of people that are being infected at every step. And so the number of infections is going to trend towards 0. And eventually you will get towards 0, and the infection will be completely eliminated from the population. On the other hand, if R is greater than 1, then that disease is going to spread in an exponential fashion. So imagine if R is equal to 1.1. Well, if R is equal to 1.1, what that means is that if you start off with 100 infected people in the population, then those 100 people are going to infect 110 other people. And then those 110 are going to infect 121 other people. And so the infection is going to spread in an exponential fashion. So it's obvious that in order to rid the population of this infectious disease, we would need the effective reproductive number to be below 1. And if we can keep it below 1 long enough, this population will be completely rid of the disease over time. And so if this is the condition that we require to rid ourselves of this disease over time, it must also be true that if we take the basic reproductive number times 1 minus the immune population, and we set this less than 0, or rather less than 1, then we are also going to rid ourselves, or rather we're going to rid this population of the disease, because R naught times 1 minus Y is equal to R. And if R is less than 1, then we are going to rid this population of the disease. So it must be true that if we take R naught times 1 minus Y, and we set that less than 1, then we are also ridding this population of the disease. This disease will peter out. Now let's have a look at this equation, and let's rearrange it to solve for Y, the fraction of the population that is immune to infection. So let's just have a look at this equation and divide both sides of this inequality by R naught, by the basic reproductive number. So I'm just dividing the left-hand side and the right-hand side by R naught. So what you're going to end up with is 1 minus Y is less than 1 over R naught. Now, we don't have to change the inequality sign here because R naught is the basic reproductive number. It is the number of people on average that an infected person would infect if everybody was susceptible. And so this has to be greater than 0 by definition. You can't infect less than 1, or you can't infect a negative number of people. So this has to be greater than 0. And so if I divide both sides by a positive number, I don't switch the inequality. Now let's subtract 1 from both sides of this inequality. I'm just subtracting 1 from the left side and from the right side. So we are going to end up with negative Y is less than 1 over R naught minus 1. So by subtracting 1, I get rid of this 1 on the left-hand side, and I end up with a negative 1 on the right-hand side. Now let's go ahead and divide both sides of this inequality by -1. So we're going to have to divide both sides of this inequality by -1. So we're going to end up with y, and now we're going to get a greater than, because if you divide both sides of an inequality by a negative number, then you flip the inequality. And then here you're going to get -1 over r, let me get the color right, r naught plus 1. Remember, we're dividing by -1, so I just added a -1 here, and then I changed the negative sign to a plus sign. And now, as the final step, let me just go ahead and on the right side of this inequality, let me reverse the order of these terms so I get the positive term before the negative term. So let me get this plus 1 before this -1 over r naught. So that's going to give me y is greater than 1 minus 1 over r naught. Now, what is this equation giving us? What is this equation giving us? This equation is actually giving you the condition for herd immunity. It is literally telling you that if the fraction of the population that is immune is greater than this, then r is less than 1, because look at what we started off with. We started off with this condition. So we had r less than 1. R less than 1. And if r is less than 1, we said that the infection will peter itself out, so the epidemic will be over. Epidemic will end with time, obviously, which is basically you will achieve herd immunity. So what this condition is telling you is that if the fraction of the population that is immune is greater than 1 minus 1 over the basic reproductive number, then you have achieved herd immunity. Now, what scientists, such as epidemiologists, are very frequently interested in is they're interested in the lower bound for this herd immunity. So they are going to set this to an equality. So they're basically going to set this to y is equal to 1 minus 1 over r naught. And what this equation is now going to give you is it's going to give you the lower bound for the fraction of the population that has to be immune in order to achieve herd immunity. So this is the lower bound. Basically, if you get over this lower bound, if the fraction of the population gets over this condition, then you will have achieved herd immunity. Now, what does this equation look like? What does this equation look like? Well, I graphed this equation, and this equation looks like this. So on the horizontal axis here, on the x-axis, you have the basic reproductive number. Now recall what the basic reproductive number is. The basic reproductive number is the amount, or rather the number of people an infected person would infect if everybody was susceptible to infection. So this is going to be disease specific. For instance, measles will have a different R naught than something like COVID-19 because these diseases spread completely differently. Some diseases are spread, using airborne particles. Some are spread using contaminated surfaces. Some are waterborne diseases. So the different characteristics of spread between those diseases is going to affect R naught. Now, another thing that affects R naught, or the basic reproductive number, are the characteristics of the population. So some populations, for instance, might have a higher number of social contacts, so a higher rate of social contacts. Some populations might live in higher density housing, for instance. So R naught is also influenced by the characteristics of the population, and R naught for any given disease will not necessarily be the same in every population around the world. R naught could be different, for instance, in the US than it is in Sweden, and it could be different in Sweden than it is in India. So this is not a fixed number. But let's assume for COVID-19, just for the sake of argument, that in some populations, say in the US, that the R naught for COVID-19 is 2.5. Well, then if R naught is 2.5, what this graph is telling you is that you will need over 60% of the population immune in the US in order to rid the US of COVID-19. So in order for COVID-19 to play itself out, and then over a period of time to rid the US of COVID-19. That's what this graph is telling you. Now, if R naught is different, so if basically the amount of people that an average infected person would infect if everybody was susceptible, if that were a different number, so if it was different than 2.5, then the threshold for herd immunity would be different, as defined by this curve. So, for instance, if we can change the disease, or we can change the population in somehow, so we can change the habits or the culture of the population somehow, to change R naught, we will essentially change the threshold for herd immunity. So let's go back to our example. Let's assume that in the US, in the very beginning, R naught was equal to 2.5. So R naught was equal to 2.5. An average infected person would infect 2.5 other people. And let's now assume that we have induced a cultural change in the US. We have convinced everybody in the US to wear masks. And let's say masks are 50%, or rather reduced infectivity by 50%. So let's say masks make it half as likely to contract the infection. That will essentially mean that we can take R naught and divide it by 2. So now the R naught is now not 2.5 anymore because everybody is wearing masks. So R naught is now 1.25. And if R naught was 1.25, then we would just need a little bit over 20% of the population immune in order to rid ourselves of COVID-19, if we can continue to convince people to wear masks. So that is a huge difference. Without masks, the R naught for this population would be 2.5, and you would need over 60% of the population immune in order to rid yourself of COVID-19. With masks, if you can get the R naught value down to 1.25, you would just need over 20% of the population immune to rid yourself of COVID-19. Now, obviously, this is just an example, and I'm not suggesting that the R naught of COVID-19 is 2.5. This is just an example. And I'm also not suggesting that masks reduce the probability of infection by 50%. But if this were the case, then this diagram basically explains itself. You would need only a little bit above 20% of the population immune, and we would be out of this crisis and COVID-free in the US. So that is the connection between the basic reproductive number, R naught, and the threshold for herd immunity.